In this video, I would like to discuss with you how to choose noise parameters and how to evaluate this choice. This is not only related to the unscented Kalman filter, but it can be applied to any Bayesian filter. When we talked about our process and our measurement models, we introduced several sources of uncertainty. In the process model, we introduced the process noise ν_k, and in the measurement model, we introduced the measurement noise ω_k. In case of a radar measurement, this was the noise of the distance measurement ρ, the angle measurement phi, and the radial velocity ρ_. We also quantified the noise with the process noise covariance matrix and the measurement noise covariance matrix. So these are the variances of the noise, and they quantify how strong the noise is. But we haven't discussed where we get these values from. Let's start with the measurement noise. This noise describes how precise the sensor can measure. It means we have to look into the sensor manual and see how precise the sensor is. For example, we might read the radar can measure the distance ρ with a standard deviation of 0.3 meters. This means we know the value for the variance sigma ρ squared, which is 0.09 meters squared. We also have to assume the noise is wide and normally distributed, which is of course not true for some sensors. It is a little more difficult to choose an appropriate process noise. In reality, objects in a traffic environment don't move with wide acceleration noise. This would mean a driver constantly switches between gas and brake. So we really apply a strong approximation here, by assuming a wide process noise. A rule of thumb for getting useful values is the following. Try to estimate what the maximum acceleration is you expect in your environment. Let's say we want to track cars in an urban environment. Then these cars usually don't accelerate or brake stronger than 6 meters per second squared. Now the rule of thumb says choose half of the maximum acceleration you expect as process noise. In this case, we would choose 9 meters squared over seconds to the power 4 as variance for the acceleration noise. If this is a good value for you, really depends on your application. Is it important for your application to react fast on changes? Then you choose the process noise a little higher. Is it important to provide smooth estimations? Then you choose the process noise a little lower. Usually you want to know, of course, if you set up the noise parameters correctly. For that purpose, you can run a consistency check on the filter. What does consistency mean? At every time cycle, we calculate the measurement prediction zk+1 pipe k and the covariance matrix S of this prediction. Then we receive the actual measurement zk+1 for that timestamp. In this example, everything looks okay. The actual measurement occurred somewhere inside the error ellipse. But this might look differently. Imagine you set up a filter and your measurement looks like this. Here, something is wrong. You constantly underestimate the uncertainty of the predicted measurement. This means your filter is not consistent. Of course, these are all stochastic processes, and it might just be a natural coincidence. But if the results keep looking like this explanation is extremely unlikely. This result tells you that you underestimate the uncertainty in your system. Your estimate is less precise than you think. The same can happen in the other direction. Look at this example. Here you overestimate the uncertainty of your system. It means your estimate is actually more precise than you think. So this filter is also inconsistent. A filter is consistent if it provides a realistic estimation uncertainty. It is very easy to check the consistency of your filter, and I recommend to always do that when you design a filter. An important consistency check is called NIS. It means normalized innovation squared. This is how the NIS is calculated. Its meaning is very intuitive. The innovation is the difference between the predicted measurement and the actual measurement. And normalized means you put it into relation to the covariance matrix S. That's why you have the inverse of the matrix S here. The NIS is just a scalar number and super easy to calculate. But you need to know what number to expect. For that, you need to know something about the statistics of this NIS. The NIS value follows a distribution which is called chi-squared distribution. If you Google chi-squared distribution, you will find a table like this. And this table tells you the number you should expect for your NIS. Let's find the right number for our example. df means degrees of freedom. That's the dimension of our measurement space. We have a three-dimensional radar measurement. So we have 3 degrees of freedom. So what do all these numbers mean? 0.95 says, statistically, in 95% of all cases, your NIS will be higher than 0.352. And this column says, in 5% of all cases, your NIS will be higher than 7.815. Let's remember this number, 7.8. What you can always do when you design a filter is plot the 95% line. In our case, that's 7.8. And then, for every time step k, calculate and plot also the NIS value. If you see something like this, then everything looks great. Sometimes you are over the 95% line, but that's what we expect. If you see something like this, it means you underestimate the uncertainty in your system, like in the example we saw before. If you see something like this, it means you overestimate the uncertainty in your system. Your estimations are actually more precise than you think. Unfortunately, the NIS test does not tell you where the mistake comes from, but it gives you at least some feedback. In this case, for example, it might be a good idea to reduce the process noise a little bit and try again. In the project, at the end of this lesson, take a look at your NIS and use it to check your process noise settings.